Hello and welcome back to Miss Sogram's Maths. This is another one in the series of D&D Resource Worked Solutions. So thank you to them for allowing me to use their materials in this way. There is a link in the video description to their website where I strongly recommend that you order a paper copy of these materials if you don't already have one. It's excellent practice for getting ready for these externals and actually going through writing them out on paper before you watch my walkthrough tutorials on this. Okay, so this one is for probability distributions, which is standard 91586. It's a stats external, and we are looking at their practice external assessment number 4 from their booklet. Okay, so on to question 1. And as always, you should highlight as you read information in the question. So we're given some information on snow depth, where we have a 217 centimeter mean with a standard deviation of 62. Now we're going to work out the probability that the average snow depth at Spencer's Creek is outside of the range of 180 to 225. So we're using a normal distribution. And we've got a mean of 217 and sigma is 62. We want to know the probability that it falls outside of 180 and 225. So we're looking for those two tails. So that's going to be, the probability is going to be equal to 1 minus the probability it lies between those numbers. And I've done it that way round because the calculator can do that for us in one step. So over to the calculator, we are going to the stats menu, distributions, normal, cumulative. Now our lower bound here is 180, the upper is 225, sigma is 62, and the mean is 217. So it will be 1 minus 0.2760, which is equal to 0.7240. Now for part B, we are being given an area and being asked to work backwards to find a value. So we want to know what value would cover, if we set that as the minimum amount, 80% of our winter seasons would hit that target or more. Now, I would prefer this question was a little clearer in which way round that was thinking about it, but we do need to interpret this as being 80% above a certain number. So we have our curve. We've got some number here where we want 80% of our winter seasons would hit that average or higher. So that's how we're interpreting this question, to say that this number would account for the average for those winter seasons. Because if they were more than that number, then we'd say, yes, they had met that average snow depth. Okay, so we're using inverse normal when we've got an area and we need to work backwards to find the x value. So on our calculator, we do distributions, normal, but we're going F3 for inverse normal. So we have a tail that is on the right. Our area is 0.8. Sigma and mean are 62 and 217 as we had before. And now x has got to be equal to 164.8 centimeters. And that, if we set that as being the number, 80% of our snow seasons would hit 164.8 centimeters or more. Okay, now calculate the probability that in a random winter season, the average depth of the average snow depth here is, it exceeds 2 meters. Now this is important, this word, given that it is under 2.5 meters in depth. So that means we're doing a conditional probability. So we're doing the probability that it exceeds 2, so it goes above 2, given that it is under x is under 2.5. So to work that out, we use the conditional probability formula, which is the probability that it's both of these things. So x is above 2 meters and below 2.5. divided by the probability that x is below 2.5. Now, this is in meters, but we were given the information in centimeters. So actually, we should write this as a 200, a 250. So I'll just fix those up. All right, so back to our stats menu, distributions, normal, cumulative. The top one is we're going between two numbers, so 200 to 250. Sigma and the mean hasn't changed, so they can stay as they were. And that top probability is 0.3108. We're going to divide it by the bottom one, which is if we do our cumulative, but we are going for the lower bound would be 0, getting no snow, and then the upper is 250. So between 0 and 250 centimeters, we've got 0.7025. So if we do that division, we have 0.3108 divided by 0.7025. An answer of 0.4424. Now, if you check the answers that are given in the book, there's a slight difference in what I've done. So what I did here for this less than 250, if you're doing strictly less than amount, normally you'd put into your lower bound on the stats menu. I'll just show you. If we go back to doing that one, the lower bound you'd usually put as a very, very large negative number. But because the context here is amount of snow, I've actually put it in as 0. Both of these methods get accepted if you're doing it in the exam. So if you were doing it strictly mathematically speaking, then you'd put 0.7027 in as this bottom number, which makes it this last digit change a tiny bit. You can see it only has a really minor effect on the answer, and both of those answers would be accepted. This is why it's really important to show you're working as you go through, so that examiner knows what it is that you've done along the way and is able to give you the credit. For part D, we've got the time taken to wax and edge a pair of skis, and it takes between 25 and 50 minutes, and the most likely time is 45. So this means we have got a triangle distribution because we don't know much else about it. So we've got 25 up to 50, and the most likely time is 45, so that's where our peak is. My triangle's not very level, but you can see what I'm doing here. Now, using an appropriate model, we're going to calculate that it will take the shot between 40 and 45 minutes to tune a pair of skis. So if we set 40 to be just here, then what we're doing is finding this gap, that amount of 40 to 45. Okay, so we need the height first. Now, height is all 2 over b minus a. B is 50, a is 25, so it's 2 over 25, or 1 over 12.5, if we want to do it that way. I'll probably leave it as 2 over 25, just as neat to not have a decimal inside of a fraction. Okay, now I'm going to use similar triangles. You can use the formula on your formula sheet to get heights if you want to do it that way. All right, so little triangle, we're starting with this triangle just here. That's got a base of, having a bit of a moment. So if we do 40, take away 25, that's going to be 15, isn't it? Yeah. So that's got a base of 15, and we're trying to work out this height here so we can work out the area. Okay, the bigger triangle. So if we do all the way up to 45, so 25 to 45 has a base of 20, and this height is 2 over 25. Now 15 out of 20 you can see is 3/4. So this height that we're looking for on the smaller triangle will be 3/4 of 2 over 25, because it's going to reduce by the same amount. Now that's 3/50ths. Wonder if that's a nice decimal. Yes, it is. So this one is a 0.06. 2 over 25 instantly is 0.08 if you prefer to work in decimals. Okay, so this area here, so areas will then be half the base times the height. That was 15 times 0.06. So that's 0.03. And the other triangle, half times the base times the height is 0.8. So we need the difference between them, which that's not feeling right to me. I've just gone back and checked. You can see I didn't quite type in the whole of what I should have on the calculation of the first area. So let's just go fix that up. We need to have 0.5 times 15 times 0.06. And that's a really good example of just making sure that you're being careful when you write down your answers. Check that they make sense to you. We want an answer that's reasonable. You should have an idea of that reasonableness as you're working this through, so you can spot when you've made errors. For mine, it was just that it didn't pick up that I typed in the whole thing on the calculator. Okay, so for this area that is between them, so the area between, we're going to do the subtraction of those two triangles. So the probability that it takes between 40 and 45 minutes will be 0.8 minus 0.45, which is equal to 0.35. Okay, now we've got a bit of an adjustment to the information. They find that partway through the season, something has changed, and 30% of the time they can complete the tune in under 35 minutes. We've still got the same minimum and maximum times of 20 and 50. We want to find the mode if it fits this distribution. So if we are going between 25 and 50 again, we've got 30% being done in less than 35 minutes. So our peak is somewhere to the right of 35 because this only covers 30% just here. Now our height at this point is still the same. It's still that the height is 2 over b minus a. So that's still the 0.08 that we had from up here. Okay, just the same as that. Now for this next bit, again, you can use the formula on your formula sheet, but my preferred way is with similar triangles. I just see the geometry a bit better. So we've got this little triangle here that goes 25 to 35. So that's got a base of 10, and we need to work out its height here. Let me just draw that a little bit better. We've got a height here that needs to make an area of 0.3. So 0.3 is the area. That's equal to half times the base, which is 10, times the height. So if you do 0.3 divided by 0.5 divided by 10, then that height is equal to 0.06. So then we need to work out what do we need to multiply up 0.6 by, 0.6 to make it into 0.08. So if we do 0.08 divided by 0.06, so 0.08 divided by 0.06, that height is 4/3 multiplier. Okay, so that's how many times bigger this big triangle is compared to the little one here. Now that same multiplier will apply to the base. Now the base here was 10, so 10 times 4 over 3 is going to get us 13.3. for the base of the bigger triangle here. So now all we need to do is add that on to 25. So the mode will be equal to that plus 25. Oops, I just need that as a decimal. There we go. So that is equal to 38.3 minutes. Right, for question 2, we've got a mountain road with ski season, and on average there are 5 accidents per 24-hour period. So we've got an average within a time interval. This tells us we are looking at a Poisson distribution. Okay, so now calculate the probability that in a 24-hour period during the ski season there are no accidents. So the probability that x is equal to 0 is going to be, we'll go straight over to the calculator. Even though 0 is an easy one to do, we'll just use our distributions here, and we're going across to Poisson. We're going equal to a point, so it's PPD. Our x is equal to 0, and the mean was 5, so our probability is 0.00674. And just a reminder that this e to the minus number means that you do your digits here start on the 3rd decimal place. So we've gone 0.00674. Okay, now justify the choice of this distribution. So why have we used a Poisson? And it did also say that we need to identify the parameters. So identifying the parameters here, so stating clearly that we had lambda was equal to 5, because then we're going to run through our RIPS acronym. Accidents occur randomly. They are independent of each other. The rate at which accidents occur is proportional to the time frame that we look at. And finally, the S, accidents occur singly or not simultaneously. And if required, you could possibly argue against some of those points, like accidents not occurring simultaneously. They could potentially happen at exactly the same time, but it's highly, highly unlikely. Okay, on to part B. So the company responsible for monitoring and clearing the road charges has an average of $590 per call-out. What's the probability the company earns in excess of $200,000 in call-out fees for a season that is 65 days long? So for them to make $200,000, let's just go over to here. So 200,000 divided by a called-out fee of 590 means they need 339 call-outs. So we want to work out the probability of that happening. The probability x is greater than 339 in 65 days. Now our lambda for a 24-hour period, let's just go back up and check that. We had 5 accidents in 24 hours. So in this case, we would have 5 times 65. 65 days. Oh, man. So 5 times 65, we've got a lambda of 325. I just spotted there should have been a greater than or equal to 339 just there. So then this would equal, so that probability we're working out, if we go to distributions, Poisson, we're doing cumulative. Now we want everything that's 339 or more, so I've set my x to be 338 because it will go up to and including. So it'll be 1 minus the probability that x is less than or equal to 338, which is 1 minus, where our lambda is 325, our probability is 0.7743. So that's going to be equal to 0.2257. Now, I believe that would be accepted as the answer, but you'll see in the book, they've actually suggested a different way to this, which I think is also, I think both of these are legitimate. So I'm going to show you the other way, which is when we have a large value. So since the 339 is large, we can use a approximation of a normal. And this idea came from times before we had calculators that could do these large numbers easily for you. But what we can recognize is when we're dealing with large numbers like this, we can use a normal approximation instead. So the probability that x is greater than or equal to 339, if we're turning that into a normal approximation, we need to apply a continuity correction. So this would be x is greater than 338.5 because we're looking for all decimal values that would round to 339 or more. Then when we do this approximation, the mean is what we had as lambda, 325. Sigma squared is also 325. So sigma is equal to the square root of 325. Which is going to be, let's just go back to here, square root of 325 is equal to 18.03. Okay, so then the probability that x is greater than 338.5 on a normal distribution will be, doing cumulative, our lower bound is 338.5. The upper bound is something very large. Sigma is 18.03 and the mean is 325. And we get 0.2270. Now you can see those two numbers are quite close. They only differ by a small amount on the third decimal place. And that comes about because we are using an approximation, so normal approximation to what was happening in a Poisson situation. And because the question didn't ask us specifically to use an approximation, I believe that both of these answers would be accepted as correct on the external. Right, we have a lot of information in Part C, so let's just take a scroll through it. We've got 15,000 skiers. They have an amount that they spend on their rental gear with a mean of 140 and a standard deviation of 42. We then have this table telling us the fee that they intend to give, and we are asked to fill in this table that works out the probability of them spending each amount. Okay, so we're asked to first of all fill in that table. So complete the probability distribution, and then we will calculate the mean and standard deviation on the fee amounts. So let's start with, we've got a normal distribution with the mean is $140 and sigma is 42. So working out the probability that they would spend less than 100 first, if we go to our distributions, normal, cumulative, we're going up to 100, so we need 0 is our lower amount, up to $100. And again, just talking through, I've talked about this before, but the lower amount here, if you're just doing this mathematically, most of the time we would put in a large negative number like minus 999. With this one, you can't spend minus money, so I'm putting in a lower limit of 0. The answer might come out slightly different to what's in the back of the book because of that, but both would be accepted. Okay, so upper limit of 100, our sigma is 42, and our mean is 140. So we get a probability of 0.1700. And as expected, that does differ very slightly from the answer in the book that went 1705, but it'll be because they put in that lower limit on here as being a large negative number. Okay, let's go for the next portion. 100 up to 200 gives me a probability of 0.75298, going to become 30. And then when we have a lower limit of 200 and upper limit is very large, we're going to go for 0.0766. Now, I am actually going to adjust my answer for the first one just to avoid any confusion with the next bit. But if you had put 0 in there, I think that it would be just absolutely fine. So if we put in a large minus number there up to 100, and the reason I've done that is because really this should all add up to 1, and I don't believe that it would if we didn't do that. And since our upper limit included a ridiculously large number, like you're not going to spend $99,000 on hiring gear, then we should probably include the mathematical limit that's at the bottom on this end too. Okay, if you don't though, I still believe both ways would be accepted. Okay, moving on to the next bit now, calculate the mean for the amount of fee being imposed. So the fee for this one was a $5 fee. The fee for this middle group is a $9 fee, and the fee for the end group is a $15 fee. I've taken that from this table here. I'm just rewriting it at the bottom so that I can see it all on the screen as I work through now. So the expected value of the fee, so how much they would expect to pay, we do the amount times the probability of it happening, and we add them all together. So $9 times by the 0.753 and also $15 times by the 0.0766. So we've done each amount that could be charged times by the probability that it does get charged like that. So working that through, we've got 5 times 0.01705, 9 times 0.753. Oh, I should have been adding these. 5, let's start that again. 5 times 0.01705 plus 9 times 0.753 plus 15 times 0.0766 comes to $8.01. On which I can see I've made a small mistake. I've added an extra 0 where there shouldn't be. Just going back and checking my answer. Sorry about that. So this just here should have been a 0.1705. It's worth just checking that you've input things correctly each time. And it's actually coming to $8.78. And standard deviation on the fee is, well, let's start with variance actually. So the variance on the fee is to take what we did here, but we square each thing. So it's the expectation of the fee squared minus the expectation of the fee all squared. Okay, so if we do the expectation of the fee here, so let's copy that across. I'm just going to paste it here. Oops. Oh, give me 1 second and I'll fix that up. There we go. But the difference here is on each of these, we take the fee and we square it. And then, oops, gosh, here we go. Let me just move this over. Because what we will do after that is take off the thing that we had above, which was the 8.7785 answer, and square that. Okay, so back over to the calculator. I can use what's already in there, but we're going to square each number. So that's going to be squared. The 9 gets squared, and the 15. And then we take off 8.7785 squared is equal to 5.4284. And then from there, the standard deviation is the square root of the variance. So the standard deviation for the fee is going to be to square root that answer and it's 2.33. Okay, now the rental company is hoping to collect at least $125,000 from the fee to go towards purchasing new hire gear. So we want to use the information that we've got to see if they would get enough money from that. So we had at the beginning, we were told that there are 15,000 skiers. We had it just at the top, just here. So we can use that to say how much we expect to make. So 15,000 people times by an expected fee of 8.78. So 15,000, and actually I'm going to use the unrounded amount just to make it as accurate as we can, because averages don't need to be rounded to nearest whole dollars. It's an average of how much we expect to happen. So if we multiply that by 15,000, we've got an expected revenue of $131,677.50 in dollars. So expected income from fees. So this is that's greater than 125,000. So they can expect to get enough capital. Now we should also support this with a calculation on the standard deviation, because if that's likely to deviate from that expected value a lot, then there wouldn't be much confidence in being able to meet that target. So the variance, we also have to work on variance and then square root it to get the standard deviation. So the variance on the fee for 15,000 people is going to be equal to, we have 15,000 individual people being added up rather than the thing being multiplied by 15,000. So we don't square this answer. We're just going to do 15,000 times by the standard deviation, which was 2.3299. Probably should have written that as its full bit up here, but I do still have it on the calculator. Right, so that was 2.3299. If we do 15,000, oh wait, that wasn't the variance, that was the standard deviation. So the variance was 5.4284. So 15,000 times by 5.4284 is equal to 81421.5. So then the standard deviation for 15,000 fees would be the square root of this, which is $285.34. So if we work out the difference between the expected amount 6.7 and their target, we can see how many standard deviations difference that might be. So dividing it by 285.34 is 23 standard deviations off of the target. That's huge. So because the standard deviation relatively is quite small, it's very unlikely that they would not meet that target. And so there's the full write-up of that last bit. Right, on to question 3. We've got one weekend with 2,000 visitors. 1,245 of them were skiers and the rest were snowboarders. What model would best represent the probability of X people out of a group of N people on the mountain being skiers, and then justify your choice of distribution? So we have N, a number of trials, and we're working out the probability where we've got a given proportion up here of 1,245 out of 2,000. So that makes it a binomial distribution, and we'll run through that justification. We've done lots of these now. So we set up our distribution is going to be binomial, n is 2000 and p is 1245 out of 2000. And then the reasons. So we run through our FIST acronym. We have a fixed number of trials. And of course, we are putting them into context as we do them. And the next is that they're independent. Then we have that the probability remains constant. And finally, there are two outcomes, that they are a skier or not. So skier or not, and there was nothing else. We were told they were either skiers or everybody else was snowboarders. Okay, part B. We've got a queue of 15 people using the model above. Calculate the probability that at least 12 of them are skiers. Okay, so we want the probability that x is greater than or equal to 12. It's going to be 1 minus the probability x is less than or equal to 11. So we've got stats menu, distributions, binomial, cumulative up to and including 11. The number of people we could try it on was 15, and our chance of success was 1,245 out of 2,000. So we have 1 minus 0.8773, which is 0.1227. And then part 2, comment on whether this is likely to reflect reality. So think about the justifications we made in the first part and whether any of them wouldn't hold true. Now, I'm thinking if you're going skiing, you could possibly be in a group, and so the independence factor wouldn't be there. If you're with a group of people, you're probably doing the same sorts of activities. So skiers would ski together and snowboarders snowboard together. So it may not reflect reality. I'll write something up about that now. And there are other possible answers to this question as well. Okay, part C. So we have 50% of all skiers on the mountain hire their equipment. 45% of snowboarders hire their equipment. We've got a group of 30 people where 18 of them are skiers. So we're going to have 12 of them that are snowboarders. We want, what's the probability that the majority of skiers and snowboarders have hired their equipment? So we want the probability that the skiers' hireage is more, so the majority of the skiers hired their equipment. So there's 18 skiers. We want the skiers hiring their equipment to be greater than or equal to, if it's for majority, we want more than half. So half would be 9. We need 10 or more skiers to have hired them. And the probability that the snowboarders is a majority, well, there's 12 of them, so 7 or more would make a majority. Now, for the skiers, they follow a binomial distribution where they've got 18 to choose from and a probability of hireage is 0.58. For the snowboarders, they follow a binomial distribution where they've got 12 of them and the probability of hireage is 0.54. So the skiers, the probability that skiers is greater than or equal to 10. We'll go to our binomial distribution. Exit out of this. Okay, so binomial cumulative, if we're going greater than or equal to 10, then it's 1 minus the probability that it's less than or equal to 9. So we've got a 9 in here. The number of them was 18. The probability of success is 0.58. So 1 minus 0.3236 is 0.6764. Let's do the same thing for the snowboarders. So snowboarders greater than or equal to 7 will be 1 minus that it's less than or equal to 6. So up to and including 6, they have 12 people and their chance of success is 0.45. So that's 1 minus 0.7393. So that's 0.2607. Now the probability of them both, so of both things being met, is that we times those two probabilities together. That's 0.1763. Okay, last part. We estimate that in the shop, 5% of the customers pay with cash. If the probability that at least one customer is paying by cash has got to be greater than 0.7, how many customers would need to make a purchase in the shop? So we're trying to work out what is n. So if x is following a binomial distribution where x is the number of customers that pay with cash, we've got n. We've got a probability to pay in cash is going to be 0.05. We want at least one customer, so the probability x is greater than or equal to 1 paying by cash has got to be greater than 0.7. This means the probability that x is equal to 0 has got to be less than 0.3. Now on a binomial, for the probability to be equal to 0, it means that every time the criteria was failed, so the failure probability is 0.95 because our success probability was 0.05. That was to the power of n. Every single trial of this was a failure. So that has to be less than 0.3. Now, use equation solver if you're not too good with your logarithms. And we can go to F3. And we'll have to do it as an equals and then work out which side we've got to be. So we're going to do 0.95 to the power of, we'll just call it x for easiness on this one, is equal to 0.3 and solve. Okay, so n, I'll write an equals for now because we need to figure out which side of that 2.347 we need to be on. Now, if you're doing this by logs, you can work that through straight away. But if not, then you can just try it out. So go into your stats menu, distributions, binomial. Let's do equal to 0. So if x equals 0, if we've got a number of trials as being 24, so if we go above the 23.47 with a probability of 0.05, what's the chance of it being equal to 0? So that comes to 0.29. So that is less than the 0.3 that we want. So n has got to be greater than 23.47 because we tried it out for 24. If I just exit back and if I try out 23, you'll see it goes above the 0.3. We need it to be less than 0.3. So our 23.47 cutoff, we've got to have n as being greater than 23.47. If you want to see the ways of using natural logs to do that, that's written out in the back of the book. And that's it for this paper. If you found this helpful, please interact with the video in some way, like, subscribe, comment on it. It just helps other people to find it too, puts that traffic up a little bit so that more people can find it useful like you did. Okay, thanks. I will see you next time.